This is Ham College, episode 99 for March 31st, 2023. Ham College is brought to you by ICOM. Got cabin fever? Look no further. Spring is in the air, and ICOM has just what you're looking for. Top quality base stations, mobiles, and handhelds that are perfect for working your favorite bands inside the ham shack or venturing out. Good evening, everyone. Welcome to another episode of Ham College. I'm Professor Thomas.
And I'm Dean Martin.
And we have a show lined up for you tonight, as per usual, but I don't know, this particular topic I kind of like here. But before we really get into that, do you know what's been going on?
Not too much. Just kind of hanging out at the house. Cleaning up after the storm. It wasn't like, it didn't have a lot of damage. We had a small tree down last week's storm.
Yeah.
Some of that. Not too bad, though.
Yeah. All the major stuff was north of here. So they had a rough time up there.
Yeah.
What did we talk about on the last show?
Well, let me put my glasses on so I can think about it.
Okay.
My memory works better like that.
Oh, I see you've printed out your memory.
Yeah, that's the best way. Well, it seems to me, best I can recall, is we talked about DSP filtering and other operations, software-defined radio fundamentals, DSP modulation, and demodulation.
That's a mouthful.
It is a mouthful. I had to reach way back in the memory banks for that one.
And this month we're going to talk about active filters and op-amp circuits. That'll cover active audio filter characteristics, basic circuit diagram, and operational amplifiers.
Oh boy, that sounds like a fun time right there.
It really is. I used to play with op-amps a lot.
I didn't, so at least one of us will be having fun.
You know, this would be a perfect time for you to start playing with op-amps.
Yeah, at least learning about them.
At least learning about them. They're a lot of fun. You can do so much. Anyway. Wow, I don't remember who took the first one last time around.
Does it matter?
It really doesn't.
Yeah. I'll take the first one. I don't even know what it is, but that's fine.
Well,
hold on a minute.
I think I can figure out what it is right here. What is an operational amplifier? A high-gain direct-coupled differential amplifier with very high input impedance and very low output impedance.
B, a digital audio amplifier whose characteristics are determined by components external to the amplifier.
C, an amplifier used to increase the average output of frequency-modulated amateur signals to the legal limit.
Or D, an RF amplifier used in the UHF and microwave regions. So I'm going to go ahead and say it's not D. I know enough about it to know that's not it. C, an amplifier used to increase the average output of frequency modulated amateur signals. No, that's not it either. B, a digital audio amplifier whose characteristics are determined by components external to the amplifier. I don't think that's it either. A high gain, direct coupled, differential amplifier with very high input impedance. That sounds like the answer A. It's A because it's not B, C, or D.
A?
A.
Okay. I'll agree with you. I think it's A.
That's my honorary Canadian accent.
The people in the chat room, most of them are saying A. Actually, all except the ones who are just joking around are saying A.
Okay.
It is a high-gained direct coupled differential amplifier with very high input impedance and very low output impedance. You know, that is a perfect combination there.
Yeah.
It really gets me excited. No, seriously.
You gonna tell me why?
It is. That is a very good combination. As a matter of fact, I got a little explaining to do here.
Okay, perfect.
An operational amplifier, often called an op-amp, is a DC-coupled, high-gain electronic voltage amplifier with a differential input and usually a single-ended output. In this configuration, an op-amp produces an output potential relative to the circuit ground that is typically 100,000 times larger than the potential difference between the input terminals. Op-amps can amplify both DC and AC signals. The popularity of op-amps as a building block in analog circuits is due to its versatility. By using negative feedback, the characteristics of an op-amp circuit, its gain, input, output impedance, and bandwidth are determined by external components and have little to do with dependence on temperature coefficients or engineering tolerances in the op-amp itself. Op-amps are widely used in electronic devices today, including a vast array of consumer, industrial, and scientific devices. And there are many standard op-amps that only cost a few cents. However, some more expensive ones can be up to $100 in small quantities. The amplifier's differential inputs consist of a non-inverting input, plus, as you can see on the top left-hand side, the V plus, and an inverting input, minus. Ideally, the op-amp amplifies only the difference in voltage between those two terminals. That's called the differential input voltage. The output voltage of an op-amp is given as Vout. The equation Vout equals AOL, and that it means open loop amplifier gain, times V plus minus V minus. So that's how you determine the voltage gain of an op-amp. Open loop refers to what we're seeing right here. This is an open loop amplifier circuit. There is no feedback resistor or components between the output of the op-amp and either one of the input terminals. The magnitude of an open loop gain is typically very large, 100,000 times or more. A small difference between the V plus and V minus inputs drives the amplifier into clipping or saturation. The magnitude of the open loop gain is not well controlled by the manufacturing process, and so it's impractical to use an open loop amplifier as a standalone differential amplifier. Without negative feedback and optionally positive feedback for regeneration, an op-amp acts as a comparator. If predictable operation is desired, negative feedback is used by applying a portion of the output voltage to the inverting input. You can see RF taking a little of that output and injecting it back into the input. The closed-loop feedback generally reduces the gain of the circuit. When negative feedback is used, the circuit's overall gain and response is determined primarily by the feedback network rather than the op-amp characteristics. To increase the gain in a closed-loop op-amp circuit, use a larger value of resistor between the output and the inverting input. To decrease gain, use a smaller value feedback resistor. High input impedance at the input terminals and low output impedance at the output terminals are particularly useful features of an op-amp. And you know, that's what I was just saying that kind of got me all choked up about this.
Yeah. I can see it's pretty near and dear to your heart.
Yeah, because high input impedance, if you think about it, if you don't want to load a circuit down, hook something across it that's high impedance, and it won't affect the circuit's performance or drop its voltage. And that's a good characteristic of an op-amp. We can hook it across other things in the circuit or feed it a voltage, and it doesn't put any load on it at all. And the low impedance output impedance, that's really handy there. That means you can drive a low impedance circuit or high impedance circuit with it. If it was a high output impedance, then we'd be limited as to what we could actually hook to the output of an op amp. We couldn't feed something low impedance or it would load it down. So it's a perfect combination there.
I see what you mean.
Mm-hmm. That's all I got to say about that for right now. It was a lot.
Yeah.
That was a lot. Well, have you got a question for me?
I just so happen to have one here. What is the typical output impedance of an op amp? A, very low.
B, very high.
C, 100 ohms.
Or D, 1,000 ohms. Well,
I think we had a little clue there.
I think we had, yeah, I think we did. As I was just proposing there, the op amp has a very low output impedance. So I'm just going to have to go straight to A because it really wouldn't make sense to run through all the others now because we know it's very low output impedance. Very high, that would really limit the usability of an op amp. 100 ohms or 1,000 ohms, I don't know, it can vary a little bit, but I just happen to know it's a very low output impedance. I'm saying A. The chat room, yeah, they're saying A.
Yeah, the ones that are saying
What are you saying?
A. A.
There we go. Simple enough.
Yeah, I got that from the professor a while ago, so it'd be kind of hard to miss that one.
It would that close together.
Uh-huh.
I hesitated whether or not to do that dissertation at that point.
No, it was
show.
good.
Yeah, I figured it seemed like a
it
good
may come
place.
in handy later for more than just you.
Well, yeah, maybe so. Let's see. I want to help you on this one. What is ringing in a filter? A, an echo caused by a long time delay.
B, a reduction in high frequency response.
C, particular cancellation of a signal over a range of frequencies.
Or D, undesired oscillations added to the desired signal. Ringing. D seems plausible, but let's go back down through them. I don't know the answer off the top of my head, by the way, so I'm going to have to do the usual process of elimination stuff. A, an echo caused by a long delay. B, a reduction in high frequency response. I don't think that would be considered a ringing. I don't think. C, partial cancellation of the signal. That's kind of a null, I think. So no, I don't think that's a ringing either. So we're down to A or D. I'm not sure an echo would be considered a ringing, so I'm going to go with D, undesired oscillations added to the desired signal.
I'm going to agree with you, and the chat room does too.
I don't think an echo would be considered a ringing. I don't think.
It's not?
It's not?
No. You nailed it.
Luckily.
Luckily. So it's undesired oscillations.
Yeah, I wouldn't think an echo. What is the typical input impedance of an op amp? A, 100 ohms.
B, 1,000 ohms.
C, very low.
Or D, very high. What is the typical input impedance of an op amp? Well, I'm going to rule out A or B right automatically because the input impedance of every op amp is not necessarily exactly the same impedance. So that leaves us very high or very low. And as we were discussing earlier, having a very high input impedance is really a nice thing because the op amp won't load down the stage before it. So I'm going with very high, and because I just happen to know that from playing a lot with op amps in the past.
Well, Professor told you a while ago.
Well, he did. He did. And it was some mighty fine reading material there from Wikipedia. And it is very high. I got a good one here for you.
Ooh.
What is meant by the term op amp input offset voltage? It's getting interesting now. A, the output voltage of an op amp minus its input voltage.
B, the difference between the output voltage of the op amp and the input voltage required in the immediately following stage.
C, the differential input voltage needed to bring the open loop output voltage to zero.
Or D, the potential between the amplifier input terminals of the op amp in an open loop condition. Ooh. I'm going to go with the A, although I kind of think maybe it might be D, but I'm not sure. I don't fully understand the D answer, so.
Okay.
See? Wow, I was way off on all of it.
Yeah, most of them said it was C. Mike kind of wavered back and forth and finally settled on C there.
That was tough.
Yep.
I need to go lay down for a minute before we go to the next one.
So, what are they talking about there?
What the heck are they talking about?
Well, you know, we looked at the op amp earlier and it had a negative and a positive input.
Yeah.
If you're looking at the output voltage, you want it to be zero. You would think, well, the positive input and the negative input should have the same exact voltage in, you know, perfect world, except one's positive and one's negative, and it would be zero at the output of the op amp. However, that's not always the case, and there's a little offset between the two. So it might be you need a voltage that's just slightly more positive on the positive input to bring the output to 0 volts. So it's like they've got to be offset a little bit. In other words, you couldn't put the exact same voltage in both inputs and get 0 on the output. Typically, I mean, if everything was perfect, you could, but it's not. So that's why we have offset voltage on the input.
How can unwanted ringing and audio instability be prevented in an op amp RC audio filter circuit? A, restrict both gain and Q.
B, restrict gain but increase Q.
C, restrict Q but increase gain.
Or D, increase both gain and Q. How can unwanted ringing and audio instability be prevented in an op amp RC audio filter circuit? All right, gain means the gain or the voltage level or volume or however you want to say it. Q is the bandwidth. Mm-hmm. And the higher the Q, the narrower the bandwidth. So if we're trying to prevent ringing and instability, I'll start at the bottom. D, increase both gain and Q. I would say that's a very bad idea, because if you increase the gain and the Q, which means narrowing the bandwidth, you could be opening yourself up to cause ringing right there, because you could possibly be causing an oscillation because you put a lot of gain into a really narrow bandwidth. C, restrict Q but increase gain. Well, increasing the gain, again, you know, if the thing is ringing and you increase the gain, that's not going to help prevent the ringing. B, restrict gain but increase Q. Well, restricting the gain's a good idea, but if you're increasing the Q, you're
making it more narrow.
You're making it more narrow, which means it would be more resonant, more likely to ring. So I'm going to say it's A, restrict both the gain and the Q. The gain and the bandwidth. Oh, makes sense to you?
Yeah, it does. It does. So I'm hoping everybody's watching this because it didn't until then.
Okay.
Like I had no idea which one it would be really. So.
Well, that's my guess.
It's not something that unless you're really into electronics and audio circuits and stuff like that you would really have exposure to. So
it doesn't really come up in everyday conversation. So I'm going to say A. And it is. And the chat room, a little mixed on that one.
Welcome to my world.
You could pick the wrong answer. It could happen.
I've seen it happen.
And it seemed like B was a pretty popular wrong answer on that.
Yeah.
And yeah, but it's restrict both the gain and the Q. Yeah. All right.
Learn something on every one of these.
Yeah.
Kind of like being in college.
Boy. Where'd you get that idea?
I don't know. It just kind of came to me.
All right. What do you say we take a quick break?
I could use one.
Got cabin fever? Look no further. Spring is in the air, and ICOM has just what you're looking for. Top quality base stations, mobiles, and handhelds that are perfect for working your favorite bands inside the ham shack or venturing out. Want to catch a sneak peek at the upcoming ICOM IC905 SHF release? From May 19th through May 21st, hams can find ICOM at booth 2608 in Building 2 at this year's Dayton Hamvention in Xenia, Ohio. Hope to see you there. ICOM's newest FM transceiver is the ICV3500, and it's ready to hit the road whenever you are. With a compact body and simple interface, this radio is a must for those looking for a long-range mobile with a fresh look. Go further with 65 watts output and get louder with 4.5 watts of audio with the ICV3500. The rugged ICOM IC-T10 portable meets or exceeds standard military testing. With an IP67 waterproof rating, the IC-T10 can withstand any field activities ahead. Hear any transmission and listen to FM broadcast with a loud 1500 milliwatt speaker. The IC-T10 is an excellent choice for any bug-out bag. The IC7300 is a high-performance, innovative HF transceiver with a compact design that will far exceed your expectations. This innovative HF transceiver digitizes RF before various stages, reducing inherent noise in different IF stages. With RF direct sampling, the IC7300 changes the way entry-level HF is designed. The IC705 is a perfect sidekick and QRP companion. Base station features and functionalities at the tips of your fingers in a portable package covering HF, 6 meters, 2 meters, and 70 centimeters. This compact rig weighs just under 2 pounds with RF direct sampling for most of the HF band and IF sampling for frequencies above 25 megahertz. The perfect accessory for the IC705 is the optional backpack LC192 with a special compartment for your IC705 and room for accessories. The ID52A is a VHF-UHF dual bander with D-Star and FM dual mode functions and is the first handheld amateur radio with a full-color 2.3-inch waterfall display. This radio supports conventional FM communications and D-Star simplex, repeater, regional, and worldwide calls over the D-Star Internet Gateway. Send photos over D-Star with a connected Android device. The ID52A is a perfect companion to the IC705. Both use compatible batteries and headsets, and you can also use the same Android app for D-Star operation. Learn more about these and all the great ICOM radios at icomamerica.com/amateur. That looks like a Ham Crew t-shirt.
It's the brother to my shirt I've got on.
It is.
Ham Crew t-shirt. Same first. Look just as good when you're leaving the Ham Fest as when you got there. Just like me.
Yep. And who wouldn't want to look like Tommy? I mean,
That's what I'm saying, brother. That is what I'm saying.
if you would like to win one of those, all you got to do is send an email to hamcollege@AmateurLogic.TV and tell us what your name is. You can put a message in there as well if you'd like. Tell us a funny story, or say hi, or just say my name is. Whatever. And we're going to do a drawing once a month of the pool of emails that we got.
Do I have to be a ham?
You don't have to be a ham.
Oh.
We got a winner.
All right. Just as easy as that. Could be you next month if your name is not.
Hi, guys. N5YWP, Reese. We know Reese.
Yeah. Saw him at the Ham Fest this year.
Yep.
First time I've seen him in a long time.
Yep. Cool.
Well, cool. Congratulations, Reese.
Yeah, congratulations. At the next Ham Fest?
We'll be looking for you.
Yep. Coming and going.
So if your name wasn't Reese and you'd like to win, haven't won one before, so send your entry in. HamCollege@AmateurLogic.TV.
I picked out an easy one just for you right here.
Appreciate that.
What is the gain bandwidth of an operational amplifier? Well,
You pulling my leg, man.
Maybe it's
You wouldn't pull my arm with a guy with a sore arm, would you?
A, the maximum frequency for a filter circuit using that type of amplifier.
B, the frequency at which the open loop gain of the amplifier equals 1.
C, the gain of the amplifier at the filter's cutoff frequency.
Or D, the frequency at which the amplifier's offset voltage is 0. What is the gain bandwidth of an operational amplifier? The maximum frequency for a filter circuit using that type of amplifier. Frequency at which the open loop gain of the amplifier equals 1. Gain of the amplifier, filter's cutoff frequency. Frequency at which the amplifier is offset. Offset voltage is 0. We just talked about that. I don't. No, I'm going to go with D. I don't know.
Okay.
Let me say, wait, B. Everybody else said B.
Well, is that allowed, though?
What?
Looking at the chat room's paper.
No. Well, yeah, after the fact. I figured you were going to let me have my paper back in an eraser to fix my answer.
Well,
yeah.
It's an exciting evening. You notice that I didn't say an answer there before I hit the button.
Yeah?
Yeah. But it is B. I'll say that now.
After you see the yellow mark?
Yeah.
You didn't know the answer either?
I thought it was B, but I'm a little divided on it.
These are a little tougher than I thought they were going to be.
Yep.
What magnitude of voltage gain can be expected from the circuit in figure E7-3 when R1 is 10 ohms and RF is 470 ohms? A, 0.21.
B, 9.4.
C, 47.
Or D, 24. What magnitude of voltage gain can be expected from the circuit in figure E7-3 when R1 is 10 ohms and RF is 470 ohms? There is a formula for figuring such things.
Say it isn't so.
It's the truth. The feedback resistance, or RF, divided by the input resistor, R1.
Okay.
So that would be 470 divided by 10. The answer is 47.
Oh, yeah, it's pretty easy on that one.
Well, if I got it right. And it is. It's 47. It's what the chat room say.
They didn't.
Some of them said C. All right.
Now they did.
Mm-hmm. That's a good formula to remember
Okay.
if you're taking the test,
Definitely.
which we just happen to be doing tonight, sort of. So I got a question for you.
Okay.
How does, it won't help you this time around though, remembering that. How does the gain of an ideal operational amplifier vary with frequency? A, it increases linearly with increasing frequency.
B, it decreases linearly with increasing frequency.
C, it decreases logarithmically with increasing frequency.
Or D, it does not vary with frequency. How does the gain of an ideal operational amplifier vary with frequency? Everybody knows D, it doesn't vary with frequency.
Okay. I'll agree with you. Not everyone does, but
Well, I didn't either. I just made that up. And then I just looked at the thing to
well,
see after. I looked at that after I said that.
are you sticking with that?
Yeah, I'm going to stick with it, D.
Well, it is. And the key was ideal operational amplifier. If it's ideal, it wouldn't vary with frequency at all.
Yeah. What will be the output voltage of the circuit shown in figure E7-3 if R1 is 1,000 ohms, RF is 10,000 ohms, and 0.23 volts DC is applied to the input?
Okay, I'm going to have to do some extra ciphering.
Yeah. You're going to have to do some gazentas.
All right. First thing I'm going to have to do is calculate the voltage gain of the amplifier. So that is going to be RF divided by R1. And let's see.
RF is 10,000 ohms.
10,000. Okay.
R1 is 1,000.
10,000 divided by 1,000 would be 10. So that's the gain of the amplifier.
Okay, I'll buy that.
Now we've got 0.23 volts times 10. That's going to make it 2.3 volts. And looking at the circuit, R1 and the feedback resistor are tied to the inverting input, the negative input. So I'm going to say that's going to be a minus 2.3 volts. I'm going to say the answer is D. Chat room's kind of all over the place on this one.
Yeah.
Let's see. I hope I'm right. So you see how I got that answer?
Mm-hmm.
Okay. I don't know that question will come up again tonight, but
Thus, if it does, I hope it's time after next.
what absolute voltage gain can be expected from the circuit in figure E7-3 when R1 is 1800 ohms and RF is 68 kiloohms? A, 1.
B, 0.03.
C, 38.
Or D, 76. I divided 1800 by 68,000 because it's kilo ohms. And I got 0.26, which should round up to 0.03. So I think it's going to be B. Unless I just blew it.
Oh, it's not a good night for ciphering.
Oh, I did it backwards.
Yeah.
Oops. Rookie mistake.
Yeah. Feedback resistance divided by the input resistance. 38.
Yeah. Gonna have to pour some water on this buzzer.
It is getting a little warm.
Yeah.
I'll have to recharge the battery.
What absolute voltage gain can be expected from the circuit in figure E7-3 when R1 is 3300 ohms and RF is 47 kilo ohms? A, 28.
B, 14.
C, 7.
Or D, 0.07. All right, I'm going to just grab a nearby calculator here. RF is 47,000 divided by the R input, or R1.
3300.
14.24. It's B. Okay.
Now all the bees are coming rolling in. It's funny how that works like that.
Yeah. So more or less that same question came up 3 times in the question pool, just with different numbers.
Yeah.
So
that's an important one to know.
Yeah, you'll want to remember that formula because good chance you're going to get one of those questions.
Oh, yeah. It's a 3 buzzer night.
It was a 3 buzzer night. Yeah. What can I say about that? Well, I do have something to say about op amps.
Okay.
But before I do it, why don't we stretch our legs for just a second?
That sounds great.
And if you'll unplug that buzzer over there,
yeah,
we'll be right back.
Around the 15th of each month, it's Amateur Radio's original and longest-running video podcast, AmateurLogic.TV, with hosts George Thomas, Tommy Martin, Emil Diodene, and Mike Morneau. Roughly, here's what I have. The bottom trace here is ground.
While the elements will jiggle some, they're actually not too bad. It's light.
After putting it together, I decided to test everything, so I ran in 12 volts, and I'm measuring the output here.
No, it's not too windy right now, Jim. It was yesterday.
We're in the antenna switching matrix. Any one of our 6 broadcast transmitters could be connected to any of the 22 antennas.
I personally am so thrilled that George got the special award. Well deserved, my friend. That's really cool.
Yeah,
What about the Super Bowl, Emil? Did you go to the Super Bowl, or were you at home operating that night?
Tuning my amplifier, and I lost power in the shack, and went outside. The house lost power, and the whole neighborhood went out for about 30 minutes. I don't know what happened.
Wow. That explains a lot. Now we can take this and put it over inside our box. It's flush to the bottom. If we were to rotate, we can see that thing goes all the way through. So we'll have a hole in the bottom.
What ammunition do you use in there?
Actually, you can use black powder. You can use WD-40. You can use, anything combustible. You just have to use the right quantity, and we assume no responsibility for mishaps.
Here's what it looks like after I've got them all soldered together and heat shrinked up. Okay, let's give it a try and see how it worked out. So there you have it, the hula loop. No, you can't null out the dogs barking.
I have 2 thin film solar cells to run this. Looks like a little mini weather satellite, actually. And I'm using guitar string for the antennas.
I particularly like that last one there, $29.99. You can get a 50-foot garden hose extension cord combo.
Do not get cord wet.
Now, most of these J-poles are built with metal elements or tubing. The reason I chose wire for this one is the length of this particular one, so I wanted to hang it from the tree so I can hoist it up there.
Yeah.
Go fishing.
Well, we couldn't find the reel.
Yeah.
Is that what that is?
All right, Tommy, sing the theme song here.
It's going to be field day here before you know it.
Yeah, it is. And it's going to be Hamvention before you know it.
Yep.
It's coming up in the middle of May.
Yeah. I'm still not sure if I'm going to make it or not.
Yeah. Well, I'm already booked, so I will be there. So I had something more to say about op amps.
Enlighten us, Professor.
Well, right here are 2 op amps. Now the one on the left, that circular can there, That is, well, it's an amputee. The legs have been cut off. They didn't copy over very well. That is probably the most popular op amp and one of the first integrated circuit op amps, the 741. The left side was very popular. That was in a can. And then on the right-hand side, that's 741 in a dip package. But it's essentially the same amplifier. So many circuits were built with these. There are better op amps around now. This was one of the earlier ones. But that is one of the basic building blocks of just about anything analog. Because it's such an eloquent design, it's very simple. You know, there's only like 8 legs on the thing. And we looked earlier, you know, at what you had, a negative and positive input, negative and positive voltage, and an output, and a ground.
Yep.
So what do
Two
you
to
think?
spare.
So what do you think is in that 741?
That's a good question. I was kind of wondering that earlier.
Well, I was kind of wondering that too, but here it is.
Oh, so you busted it open, huh?
I busted it open, and this is what I found in there. A schematic printed.
Wow.
A small-scale integrated circuit, the 741 op amp shares with most op amps an internal structure consisting of 3 gain stages.
Mike says it's got smoke in it.
It does. Number 1 is the differential amplifier. That's outlined in dark blue. It provides a high differential amplification gain with rejection of common mode signals, low noise, and high input impedance. And that drives number 2, which is a voltage amplifier that's outlined in magenta. That provides high voltage gain, a single pole frequency roll-off. That drives number 3, which is an output amplifier. That is outlined in cyan and in green, and that provides high current gain, low output impedance, along with output current limiting and output short circuit protection. And additionally, there is a current mirror that's outlined in red, and bias and compensation capacitor of 30 picofarads. 22 transistors in one of those little packages.
Wow.
Along with all the interconnecting resistors. And you'll notice capacitors, there's only that one 30 picofarad capacitor. The signal comes in on the left-hand side at the input. It never goes through a capacitor. That means you can put in a DC voltage at the input and get a DC voltage at the output. It can amplify AC or DC. And that one capacitor in there is a compensation condenser. The signal doesn't actually have to pass through it. I thought that was quite interesting.
Yeah, it's pretty cool stuff. I was thinking about it earlier when we first started talking about them. And those things remind me a lot of my job, or well, used to my job, but writing components, objects, that basically a library or whatever, then you just has certain inputs. You get exactly the output on it. It's exactly the same thing. It's just electronics.
Yeah. Well, you know, interesting thing, op amps were developed to be used with analog computers.
Oh, yeah?
Yep. That's why I say that's why. I assume that's why they invented them in the first place. And, you know, it didn't just start with the integrated circuit. There were op amp circuits before that. As a matter of fact, this is not the first one, but one of the very early op amps was this right here, a tube-type version.
Oh, yeah?
In 1953, commercially available op amp. It's a vacuum tube op amp, was available and released as the model K2-W by George A. Philbrick Researches.
Philbrick?
Yep.
Is that Philco?
It's not. The designation on the device, GAP/R, is an acronym for the complete company name. It has 2 9-pin 12AX7 vacuum tubes, which were a very popular tube, still are. and they were mounted in optical packages and had a model K2P with a chopper added that was available that would effectively use up the non-inverting input. This op amp was based on a descendant of Julie's 1947 design, and along with its successor would start the widespread use of op amps in the industry. So that's quite a bit larger and potentially quite a bit hotter than those little integrated circuits that we were looking at. Operational amplifier, very handy thing. If you want to do some playing with electronics, that's a great place to start. Get you some Forrest Mims engineering notebooks or mini notebooks. Radio Shack used to sell them. They're available from Master Publishing. That's how I got to playing with them. Forrest has put all the little circuits in there. I should have had the book out here, but I wasn't thinking about it.
I've got those books. I got them from Radio Shack years and years and years ago, the little ones.
You just need to buy you a few op amps, a few resistors, capacitors. You could start playing with them.
I probably have some in the Radio Shack, those kits I bought at Radio Shack.
You
clearance.
did. Yep. There would be in there. So it's a lot of fun. If you want to build a little amplifier and just do some practical playing with electronics, an op amp is a great place to start, and doesn't take a lot of extra components, just very few. And we were looking there earlier at the op amp that had a positive and a negative voltage supply for it. You can bias that where you only need a single polarity supply. You don't have to have the negative supply. There's just a little bias circuit that you put on there. So, you can get away with just using a single voltage. So
cool stuff.
Lots of fun. And I wasted a lot of time playing with those and built a number of things
That wouldn't
too.
consider it a waste.
No, it wasn't.
Anytime you learn something, it's not a waste.
Yep. Well, I guess that's going to do it for tonight. You know, only one person was going to win that T-shirt, no matter how you stack it.
That is true.
There was only one shirt going to be given away tonight, and that was it right there. If you'd like to look cool, because it's coming up.
Who don't want to look cool?
Hamfest and Field Day season here.
It's time to get stylish, people.
Yep. And how better to do that than with one of these items right here, one of these quality items from.
Oh, yeah, you would be in style with that. shop.spreadshirt.com/AmateurLogic. We've got caps, golf shirts, T-shirts, hoodies, V-neck T-shirts. Like, there's all kind of stuff in there. There's little backpacks in there, coffee cups, plastic commuter mugs, all kind of cool stuff in there.
Yeah.
I think that shows mostly Amateur Logic, but there's some Ham College swag in there as well. So.
Yeah. Plenty of swag for your swagging needs.
For your swagger.
Yep. And if you'd like to keep up with high society throughout the month, well, you can do that at one of these fine locations right here, facebook.com/group/Ham College.
Yeah, you can follow us on at Ham College on Twitter.
Or you can join the groups.io page, groups.io/G/AmateurLogic, where you'll just be emailed a notification when there's going to be a live stream or when a new episode is released.
Yeah, that's anti-social media.
Yeah, maybe.
Yeah, you know what I mean.
Yeah. And if you need show notes, because
boy, do we have show notes.
Let's face it, sometimes you need to look up stuff.
You do. You can go to our wiki at, we have a great wiki master that keeps up with that thing. And a modest one, AmateurLogic.TV /wiki.
Yep. Join us again at the end of next month for another Ham College. And join us in the middle of the month, which is probably going to be like, March 17th, you think?
How about April? Unless we're
That's
going to wait till
even better,
next year.
since it's already past March
April
17th.
14th?
April 14th. That sounds like a convenient day.
Yeah, so everybody can be sad before they drop their taxes off.
Yep.
Oh, man.
You know, one day different, it could have been another Friday the 13th.
So close.
Can't have that every month.
It's a shame.
Yep.
Those are pretty special.
Yep. 7-3.
Yep, 7-3, everybody.
See, it decreases logarithmic. Let me try that again. See, it decreases logarithmic